All right, so I'm going to talk to you about making our way through the multiverse. This is not exactly what I work on. Hopefully one day I'll give you a talk about the dark matter simulations and galaxy formation stuff that I work on. However, this is stuff that I thought about at one point. However, if you're looking for more information, I'd strongly recommend checking out Max Tegmark's website. Some of the terminology in this talk is actually taken from some of his papers, as well as some of the images I've borrowed generously from a wonderful Scientific American article of his. Okay, so let's get started. We're going to talk about some pretty weird stuff. This is obviously from The Onion. Yeah, the text of this is great, too. It all talked about how the universe is really disappointed in this guy sitting on his couch doing nothing. So we're going to talk about some weird things, some trippy things. Parallel universes, an infinite size of the universe. Maybe some implications of string theory. One thing I just want to point out is even though these are big concepts and they're hard to wrap your head around, and sometimes you may just reject some of these ideas, everything we're going to talk about is based on science and is testifiable, is falsifiable and testable. So to get started, let's talk about, before we talk about what makes up a multiverse, we've got to talk about what makes up the universe. So Carl showed a version of this pie chart. His was prettier. So this is the ingredients that makes up the universe. About 5% of the universe is made up of ordinary matter that a standard model of particle physics can tell us something about. So ordinary matter is you, me, stars, planets, galaxies, all the ordinary stuff that interacts with light in the ways that we expect. About 25% is made up of dark matter, some mysterious substance that we don't know exactly what it is, although leading theories expect it to be some sort of very massive particle. And then last, making up the energy budget, 70% of the energy matter budget of the universe is dark energy. And this is this mysterious form of energy that's driving the accelerated expansion of the universe today. Okay, so knowing what makes up the universe, and we can talk about the history of the universe. So the universe started about 14 billion years ago in a very hot, dense ball of plasma. As the universe expanded and cooled, the protons and neutrons in this dense ball of plasma fused together to form our first nuclei. Again, the universe cools and expands. It's going to keep doing that. And eventually, those ions can capture electrons, and the universe becomes neutral. It's at that point that the primordial photons, and this is the light that's been in the Big Bang since the very beginning, can free stream throughout the universe. Before, the photons just kind of ping-ponged around and all these free electrons are sitting out there. And so once those electrons are absorbed into an atom, there's nothing for them to ping-pong about, and they can just free stream throughout the universe. And so we can actually build satellites and actually look for this cosmic microwave background, one of the images of which Carl showed in his talk earlier, and that was that oval-shaped baby universe picture that someone asked a question about. And that the CMB I'm not going to talk much about, but it's this amazing tool that tells us a ton of different things about to test theories about the universe and gives us a lot of information about what makes up our universe. Okay, so after that period of recombination and the CMB photons begin to free stream through the universe, the ordinary matter begins to fall into the dark matter halos that have already begun. The dark matter halos have already begun to collapse, and the gravitation from those objects can pull in the ordinary matter, the gas, that falls into the center of these dark matter halos. And as it does, those particles collide and they heat up. And eventually, through atomic processes, that hot gas can cool and fragment and form the first stars. Those first stars form in the first galaxies, somewhere around 400 million years after the start of the Big Bang. So it's at that point we have our first galaxies in the universe. And so for the remaining intervening history of the universe, those baby galaxies are going to collide and merge and form much larger galaxies like our own Milky Way spiral galaxy. So eventually, 13.7, or to round off 14 billion years later, we find ourselves here at today, where we've begun to notice that the universe expansion is starting to accelerate due to dark energy. And we find ourselves in the standard model of cosmology in an infinite universe. Okay? And so generally when you hear that astronomers talk about our universe, what they're actually talking about is our observable universe, which is the finite volume within this infinite universe that we can actually observe. And so if you're not buying the idea of infinite, it's at least so big that mathematically it's a safe assumption, we'll just say infinite for the purpose of today. Okay, so if we have a finite volume that we can observe, we actually have at the edge a horizon. a limit to which we can't see beyond. And you're all familiar with horizons. If you've ever been on a boat out in the ocean and you've gotten far enough away from land, you find yourself just surrounded by water in all directions. And you know that the Earth doesn't end where you can see it continues on beyond that horizon. But the limits that you can see are set by the curvature of the Earth. The Earth is curved, and we can actually find the distance to that horizon, the farthest that we can see, by using some simple geometry and figuring out what the farthest distance it is. We're not going to work through this. That's a take-home question for all of you to figure out whether there's any mistakes in the Google image I brought down. To be honest, particularly for everyone watching YouTube, I didn't check this at all, so no idea. Okay, in the universe, though, the horizon, the furthest distance that we can observe, if I trip up and say C is a bad term. We want to use observe because C means visual light. We can observe all ranges, frequencies of light. So the furthest distance we can observe is set by a couple factors. One, it's set by the finite speed of light, the fastest that any object can travel in the universe. The time since the Big Bang, about 14 billion years. There's a number that's wrong. That's 10 to the 8. It should be 10 to the 9. My bad. Yeah, sorry. You find me later and beat me up. And then there's also the expansion factor. As the universe, over those 14 billion years, the universe has been expanding. And so if you're going to send light signal from one place in the universe to another, you got to know that the space in between is going to expand as that light signal travels. All right, so in the end, the size of the observable universe that we can actually measure and probe and make experiments in is 4 times 10 to the 26 meters long. Yeah, it's a gigantic number. But the question is how big is that really? I don't have any really good feel for this. It's really huge. Right, so a meter is basically a yard, and there's 100 yards in a football field, so this is 4 times 10 to the 24 football fields. That's the best I can do. That's generally what I think of, because I'm a dumb American. All right, so let's get some perspective. How big is this? All right, so here's the famous blue marble image that's taken by the Apollo 17 crew on their way to the moon, and at this point, the astronauts were 45,000 kilometers from the Earth. The Earth is obviously orbiting around the sun, which at the edge of the heliosphere at 100 AAU, you're at 15 billion kilometers away, which takes light to travel about 14 hours. And that sun is one star in billions of stars in the Milky Way disk. This is actually an image of Andromeda. Our sun is about halfway out to the edge of the disk, orbiting around along with all these other stars and gas. And the width of the Milky Way galaxy from end to end is about 10 to the 18 kilometers. Again, we're starting to lose a concept of what that physically means. So 100,000 light years. It takes light 100,000 years to travel from one end to the other. Okay, if you could actually see dark matter, this is what you would see. Surrounding our Milky Way galaxy and all galaxies is a large dark matter halo, which is basically, you just think of the galaxies are at the center of a large gas of dark matter particles. And this giant halo of dark matter is gigantic. This is to scale. So I shrunk that image down to the size it would be in the dark matter halo. So that's how tiny it is in respect to the dark matter halo. The Milky Way's dark matter halo is about 3 million light years across. In this image, this is a false color image. It's an image of a simulation done on a computer, one of the things that I do. Every pixel, the brightness of a pixel in this image corresponds to density. So the brighter points are denser. So these are dense clumps of dark matter. Dark matter doesn't exist in an empty universe. It's within a giant cosmic web of dark matter. And so in the center of this is a giant cluster, or there would be a giant cluster of galaxies living in this huge dark matter halo, hundreds of galaxies, maybe thousands. And in the center would be a very massive galaxy. And you notice that there's these filaments of dark matter that are intersecting at this halo, and dark matter is flowing into it. And so there is our massive Milky Way halo, somewhere in some filament far away from this big guy, since it's a little more isolated than this image makes. I just threw this in there. This isn't exactly our dark matter distribution. I'm just trying to give you some scale. Okay, so if we were to continue to zoom out, that number is 145 million light years. As we move out, you'll notice that this filamentary structure repeats, and that there are these large underdense regions, or voids. These are hundreds of millions of light years across. And so as we keep zooming out, you'll notice at some point, everything in one section of the universe looks pretty much similar to everything else. It's hard to point out. If I gave you this snapshot here, you'd have a hard point of going, that's that part over there. And so this is the principle of homogeneity and isotropy. The universe is pretty much has the same amount of matter and looks the same in all directions. So finally, we get out to this section. So now let's put this back into our first image. So here is this within the size of the observable universe. Okay. So that number, now you have some idea of exactly how big our observable universe is. And remember, this is just our finite portion within an infinite universe. And this square doesn't sit in some empty universe. This actually fills the whole screen. So it would look more like this. Here is our horizon, and here is the dark matter that fills the entire infinite universe. So the principles of cosmology tell us that the universe is homogeneous and isotropic in an infinite universe. And so the principles, this cosmological principle is important because what it tells you is that there is no special place in the universe. There's no center and there's no edge. And what that also tells you is that every point in this, the Big Bang happened at the same time at every point in this infinite universe. That means that every point in this image is 14 billion years after the Big Bang. Okay. The other important point is that the expansion of the universe is accelerating, and there's some important implications of that other than Carl's going to go find it, win himself a Nobel Prize. There's some interesting implications for this. Okay, so imagine you're here. This is you, this blue star in your observable patch of the universe, and you have a friend who lives somewhere else in this universe. These two observers have overlapping observable patches. So these two observers can actually communicate with each other. If one observer was to look in this direction, again, there's a light travel delay, so if this is a million light years apart, it's going to take light coming from the blue star a million years to reach the green star, neglecting the expansion of the universe. And so you have to wait a very long time to actually see humans and Earth and us evolve. But that's besides the point. These two, in theory, can interact. However, at another part of the universe, if we had some orange star way off to the left of the slide, there are observable patches that don't intersect. And so in this case, we have two giant observable patches to two different observers that can never communicate with each other. And so this is our first idea of the multiverse. So this is what's referred to by Max Tegmark as a level 1 multiverse. So here we are in our bubble, 4 times 10 to the 26 meters in radius. And next door is a parallel universe. All right, so these are the finite observable regions that are bounded by each other's observers' horizons. In an infinite universe, there's an infinite number of these finite volume patches, right? And so if you were to think about it, if you considered all the protons that are ordered in our universe, if we just reduced all the matter in the universe to the number of protons, so 10 to the 118, all right, and you think about our universe is just some configuration of those protons, the next universe over should have the same amount. However, there could be a rearranged slightly. All right, so eventually we'll reach an observable patch as we move on in this infinite universe that has the exact same orientation of those gigantic number of protons. It's a really, really huge number. But in this infinite universe, technically, there should be an infinite number of universes exactly, very similar to ours, or almost exactly. So there's an infinite number of Earths that look just like ours, and there's an infinite number of U's. All right? However, in those infinite number of views, maybe there's a slight decision that happened along the way that was different. So maybe you decided to get bangs the last time you got your hair cut. Maybe you decided not to come to Astronomy on Tap in this other alternate universe. So that's good to know, because if you ever meet your doppelganger and you get in a fight, you're gonna be a little bit smarter, know a little bit more, and you're gonna win that doppelganger fight. Okay, so this is our first level 1 multiverse. So to think about the next level of multiverse, we need to think about how to grow a universe. All right, so I'm going to talk very, very briefly and on a very surface level about the theory of inflation, which talks about how the Big Bang gets started. Where eventually, we've talked to a grad student, we're going to have someone come and give a really great detailed talk about inflation, how it's tested, all the predictions it makes, and all the things that have been confirmed through observations, and also what's left open. So what the theory of inflation proposes is that before the Big Bang, there was an infinite empty universe, empty in all ways with the exception of a scalar field. And the scalar field is called the inflaton in these models. And essentially what this scalar field does is it acts like a vacuum energy. It's just like dark energy. It's driving an accelerated expansion of the universe. So there's nothing in this universe except this vacuum energy that's driving this rapid expansion. And so in this infinite, internally expanding universe, some small finite volume can actually possibly quantum tunnel or quantum fluctuate into a baby universe, or a bubble universe as it's drawn here. So this parent universe, which this is infinite, I've just drawn a tiny circle, spawns some child universe. here. And in that child universe, you're basically going from one level of vacuum energy to a slightly lower level of vacuum energy, at least in this example that I'm going to give you. So that slightly lower level of vacuum energy, it still has a vacuum energy, and so that will also be expanding. So some of that energy will go into a rapid expansion known as inflation. That's what's given here. So there will be a rapid expansion of inflation, and then some of that energy is going to get dumped into converting that energy into matter and radiation. So some of that energy gets dumped into starting the Big Bang off. So in this daughter universe, a Big Bang can be created, and then here we are today. Okay, so you can think about this vacuum energy as a false vacuum. And so here's our infinite inflating universe to start, and then a bubble universe pops out of it. But what's surrounding this bubble universe is more infinite inflating universe. And so we're not special. There's no one place in the universe that's special. So not only can our universe pop out, but other universes can pop out. And since this is an infinite and expanding universe, more universes can pop out, and so on and so forth. And so this is our level 2 multiverse. So our level 2 multiverse is level 1 universes, infinite universes of which we're this small, gigantic volume. This is our observable, the patch we can observe within this infinite, accelerating, expanding universe. What's interesting about the level 2 universe is within higher level models of particle physics, the fundamental constants aren't fundamental. So the mass of the proton, the mass of the electron, the relative strength of forces, even the number of space-time dimensions in string theory isn't a fundamental thing. So the fact that we have 3 dimensions of space and 1 at a time isn't necessarily fundamental. This is all set by some sort of symmetry breaking early on in the universe. So these other level 1 universes could have different fundamental laws of physics. They could have different dimensions of space-time. They could have different mass of the proton, different levels between the strength of the force of gravity versus the strong force, et cetera, et cetera. So these universes are completely different than these universes here. Okay, so I'm going to quickly wrap up. What's interesting is, so here we are. Our universe is expanding. The horizon that we can observe is also growing. But we have this amount of dark energy. So what we thought that the expansion of the universe over time would actually slow down. The mutual attraction of gravity from all the matter in the universe would slow the expansion of the universe at time, possibly causing it to recollapse, possibly just causing the expansion to slow and get smaller and smaller and smaller. But because we observe that there's some amount of dark energy in our universe, we know that the fate of our universe is actually this. The rate of expansion is actually accelerating. And a fate of that is that eventually our ultimate fate is to end in a big chill, where all the matter in the universe that's not gravitationally bound to our own galaxy is going to get pushed out. So even though our horizon is going to get bigger, all the stuff in it is going to get driven out. So eventually what we're going to do is find ourselves in the center of a completely empty, infinite, inflating universe. Does this look familiar? It should. So if this dark energy, it could be a lot of different things. It could be a particle, GR could be wrong, but if it is a vacuum energy within some landscape of other possible vacua, eventually another daughter universe could spawn out of our universe. We could give birth to a whole nother universe. I drew this little bubble universe within our observable patch. It really could be really far away. It's more likely to be far away. There's no reason in an infinite universe this would be so close, but anyways, the purpose of drawing the picture. Just want to be clear. All right, so what this looks like in the chaotic eternal inflation is there's an old cosmology joke. It's just turtles all the way down. So infinite universes, each of these are infinite universes, can spawn children infinite universes and so on and so forth eternally and so on for all time. And so each of these are level 1 universes in the different colors. This is a famous image from Andre Linde, who's one of the pioneers of inflation theory. And each of these different little bubbles represents, the different colors are supposed to represent different physics that can exist. So a whole different level of physics can spawn out of one universe that has those set. Okay, that's it. Thank you.
I think you just hurt my brain.
Yeah, that was really fast. I'm sorry. There's actually 2 other levels to a multiverse, and you can go look at Max Tegmark. They actually get weirder. One's quantum mechanical, where, anyway.
Anyway, okay. Questions? Too many questions. Right in front.
Quantum mechanical universe. Would it be the one where you open a wormhole between universes? No. The quantum mechanical one is this idea that it's the Everett's many worlds interpretation of quantum mechanics, where instead of the Copenhagen interpretation, where the wave function, which describes the probability of a particle existing in some location being observed and then collapsing to a definite outcome, this means that every quantum event causes a split. And so in one parallel universe, you decided to wear a red shirt and the other blue, so forth and so on. The tunneling, the wormholes, all these theoretical proposed ideas that two black holes are connected by a tunnel and that you could maybe Matthew McConaughey your way through, right?
I'm glad that's a verb.
And as far as I know, they're unstable. I don't know much about them. No, what you would want a wormhole would be faster than light travel, which would probably only get you through our observable universe. Maybe you can get into the causal patch next door. I don't know. How does the Flash do it?
He's magic, dude.
Yeah, magic. I like magic. I like that answer. I don't know.
I think you used every physics word in that explanation, by the way.
Yeah,
All right, more questions. Whoever set up here.
At the ratio of dark matter to regular old standard matter. Is that homogeneous, observably in the universe, or is there any variability in that?
So the ratio of dark matter to the ratio of ordinary matter, is that homogeneous as well? Or is there any variability between that within observable universe? So no, it should be completely the same in all places. We've made tests of that in a lot of different areas. We've looked at clusters. The CMB gives us a strong indication of that ratio. So it should be the same everywhere in our infinite universe. I mean, really, the thing when astronomers say our universe, what they really mean is our observable universe, where we can actually conduct experiments in. And we can possibly infer what happens outside of that observable universe, but you can't actually really test that in any way, right? So what you end up doing is relying on observations and relying on that principle to hold. However, the CMB is this amazing result because the CMB is collecting these primordial photons coming from all different directions from the start of the Big Bang, right? And so when we measure the temperature is the same in all these different places. And there's a lot of reasons why that shouldn't happen, which I can't go into, but the inflation talk we'll talk about. However, what you can do is, if you notice that plot that Carl showed earlier, there was different points. So most of it's green, but there's some points that are red, some points that are blue. And what those red and blue points are is portions of the CMB that are a little bit hotter, a little bit colder. And when you look at those points, what you can do is do a Fourier transform of those points. And so what that means is it's just adding a bunch of sine functions together. Okay, so I'm going to get to the point. So the CMB gives a very strong indication that in all directions, homogeneity and isotropy holds because we measure the same amount ratio of dark matter to ordinary matter in all directions. And I probably should have just said that.
I think the answer to your question was yes.
What? I can't hear you. One more time. Oh, you love Fourier transforms. He started dancing. I thought maybe you wanted to go home. You got excited. That's good to know.
Are you an astronomer? Do you do radio astronomy? Because you should.
Okay, one more.
One more question. Shorter answers.
Sorry. All right, up there. Okay, so in the level 1 multiverse scenario, is it literally that one universe begins exactly where another universe ends? So I had all those circles touching. No, it's just a way of relating the limits to the point where we can't interact, right? So if there is an observer within that distance, they can actually communicate between each other. So that's the point when they're causally disconnected, and there's no longer any overlap in the observations they can make. So that means that there's no way for me to know by any experiment exactly what's happening in that one region right next door. And so that's why so that's a different observable universe, and so that's a different universe. Sure. Sure. Yeah. Yeah, that was something different, and I drew
What
it.
did he
Remember,
say?
so the question was: is you talked about one universe being born inside of another universe. So what that was at the very end state where we basically what we have at that point is just an empty universe full of nothing, but it so happens us, and an infinite universe just full of vacuum energy. And so I drew that circle pretty close to ours, and that's why I did that song and dance about it really shouldn't be that close, it could be far away. So to the point where we'll never observe that happening. There are some possible theoretical papers that are written about maybe we can see these other bubble universes popping up in the CMB somewhere, but so far there's no evidence of that.
Okay, I can't handle more questions, so let's thank our speaker one more time.